But specifically today we're going to be talking about limits at infinity. We want to know what's happening at infinity, or how we get a limit that equals infinity, and what it means about a graph. So our goal today, find the limit as x approaches infinity, and find the limit as x approaches c that equals infinity. So a good graph to start with is 1 over x, because it fulfills all of these things. It can have a limit equal infinity, and it can show us what a limit going to infinity can equal. So does anyone know what the picture of 1 over x will look like? It's something you should know from pre-calculus. It's going to look like this. Okay, but I see you drawing the shape. Kind of looks like this. Okay, but it also can have a negative side. It could look like this. So remember, we're trying to consider what happens to the y values as we approach some x value. So you don't have to write the questions down, these were to help me remember. What happens is x approaches infinity. So if I'm following my graph and we're following the x values to infinity, what's happening to my y values? Getting smaller. Specifically, what is it approaching?
0.
0. Now we know 0, it's never going to hit, it's never going to cross, but it's going to get close enough. Remember, we just care that it's getting infinitely close. So if I consider the limit as x approaches positive infinity of our function 1 over x, we get 0. What happens if I approach negative infinity? Still 0. Now that doesn't have to be the case. This is just a nice one because it also has some vertical asymptotes we can talk about. Okay, so let's look at what's happening when we're approaching 0. This time we have to approach from different directions because we don't have the same limit from both sides. But if I'm approaching 0 from the right, what's happening to the y values on my graph? Getting bigger. What do we call getting bigger forever? Infinity. So our limits can equal infinity. Remember, infinity is not a number. It's the concept of getting bigger forever. What if I approach 0 from the left? Negative infinity. So looking at our graph, what do we call this line that our graph never crosses? This one is a horizontal asymptote. What about if I have the line that we never cross in this direction? Vertical asymptote. So our limits at infinity all have to do with our asymptotes. Limits as we approach infinity tell us about our horizontal asymptotes. Limits as we approach a number that equal infinity tell us about our vertical asymptotes. So once again, that's more a question that I just didn't want to forget to ask. But let's talk about the calculus way first, and then we'll actually talk about the pre-calculus way. So, calculus way of horizontal asymptotes. If our limit as x approaches infinity of f of x equals some number, can be any number, or the limit as we approach negative infinity equals some number. Then we have a horizontal asymptote at y equals b. So we learned in pre-calculus the only way an asymptote ever comes up is if we're dividing. That's when we get asymptotes. And when we were dividing, we looked at the degrees of the top of the numerator and the degree of the denominator, and we compared those values. Well, now we have kind of a quicker way. We have our calculus way where we can just take the limit as we approach infinity, and that will tell us what our horizontal asymptote is. So let's look at two examples of horizontal asymptotes, and then we'll look at vertical asymptotes. So let's find all horizontal asymptotes of f of x equals x over square root of x squared plus 1. So if I'm going to find horizontal asymptotes, I've got to check these limits. I'm going to check the limit as x approaches positive infinity of f of x. Now I've got to check the limit as x approaches negative infinity of f of x. And honestly, the best way to do this is graphically. We've learned our algebraic ways of solving stuff, but I can't really plug in infinity. I can kind of think about what would happen if I had infinity, but we can't just plug it in directly, so it's better to look at it graphically. Software. Sorry, I usually load it before class.
It's setting up the main window.
It's being slow about it.
No, it's creating document workspace. Now it's populating something.
Thanks, Ben. I never remember that.
You know how in Star Trek there's that one person that just repeated what the computer says?
Was he on the bridge or was he in the engine room? Because as long as he's on the bridge, it survived.
Okay, so our function was x divided by square root of x squared plus 1. So looking at it graphically, what does it look like is happening as we approach infinity or approach negative infinity? Does it look like our horizontal asymptotes are for this? Okay, 1. Looks like when we approach positive infinity, we are hitting 1. And when we approach negative infinity, we're hitting negative 1. So we can still use some of our pre-calculus skills to help us out. So we're pretty sure 1, and as we approach negative infinity, negative 1. So we had to consider the degrees of our numerator and degrees of our denominator. So degree, we mean the power, the highest power. So what's the degree of our numerator? power on that polynomial. It's not a trick question. Power of x. 1. Okay, power of x is 1. So our degree of the numerator is 1. What about the denominator? This one's a little trickier. If I'm just looking at square root of x squared, what's the degree of the denominator?
1.
1. Okay, so we compare the degrees. We have 1 to 1. So if the degrees match, we knew a horizontal asymptote was formed by the coefficients here. Coefficient of 1 divided by coefficient of square root of 1. So can you see where we got both positive and negative 1? What if the degree of the numerator is bigger? What if this was x cubed over this? In pre-calculus, that means there is no horizontal asymptotes. And if the degree of the denominator is bigger, the horizontal asymptote is always, let me finish that. 0, the x-axis. We're going to skip the second example just because, like I said, I want to try and finish our assignment. Okay, so vertical asymptotes. We get a vertical asymptote if we have a 0 in the denominator. That's how we considered vertical asymptotes in pre-calculus. In calculus, if the limit as x approaches a from the right of a function is positive or negative infinity, or the limit as x approaches a from the left of a function is positive or negative infinity, then we have a vertical asymptote. I'm just going to write VA for vertical asymptote at x equals a. So it's just our calculus way to prove that we do have a vertical asymptote. And once again, the best way is graphically. You're going to be doing a lot of looking at graphs today. So if we had this one, we would draw the graph. Looks a lot like our 1 over x, but it's a little steeper. So what would we try and approach to check and see if it's a vertical asymptote? What should we be approaching? 0. So I would need to check the limit as x approaches 0 from the right, and the limit as x approaches 0 from the left. And if either of those equal infinity, then we have a vertical asymptote. Well, if those equal positive or negative infinity, we have a vertical asymptote. From the right, we know it's going to be positive infinity. From the left, we know it's going to be negative infinity. But we know from our pre-calculus skills that whatever makes the denominator 0, that's what we should be checking out. Right here, to make the denominator 0 would be 0. What if I had 2 over x minus 1 instead? What number should I be looking into on this? What would make the denominator 0? 1. Good. So we only have about 15 minutes, but it's a pretty short assignment. It's mostly looking at graphs. Like I said, our goal is to try and finish in class today so we don't have any homework.